I'm happy to be here today. I want to thank organizers and the conference was quite very successful from many points of view, rest of the series. So today I will speak about additive manufacturing, current trends and opportunities. In particular, I will focus on bio-inspired architect cellular materials. The umbrella of this of the presentation. Let's start with better sense about this go. Okay. So I will use this one. Oh, I will use this one. So the project is the political one. To present from here. So the umbrella of the project is Butterfly, which is a ERC finance project, where we have tried to create a super resistant fatigue structure starting from bio-inspired design. So this is the aim of the project that I will introduce today. After that, I want to say that dealing with this topic of additive manufacturing as TC15, we have organized a conference that will be held in Vicenza, in Italy, in this February, so in February 2026, and actually we will be happy to guest all of you there for discussing topic related to additive manufacturing and in particular structural integrity of additive manufacturing, which is the aim of the TC15. So I want to thank before to start all the partners, especially Sapienza for guesting the project and all the partners involved, in particular University of Trento. And also I want to thank University of Padua and the ERC, of course, European Research Council for financing this project. So which are the challenges in fatigue? It's quite evident also up to now, because if you consider the failures in structural components, more than 90% of failures happen due to fatigue or cyclic loading. And this is happening also recently, not only far away from us. And what it is interesting about fatigue is that it's touching different scale lengths. So you can actually consider fatigue at in very large structures. You can consider fatigue in micro structure, and you can consider fatigue at nanostructure. So the scale effect plays a fundamental role dealing with fatigue problems. The challenges in fatigue are still quite open, and despite it is one of the most studied problems, there are a lot of issues that are related with the fatigue design that are not well understood up to now. And there are a lot of possibility of improvements for new materials and new structures. So it is quite evident that dealing with the bio-inspired design, it is possible to solve the issue between strength and toughness. And in particular, this work with Robert Ricci has shown that there is the possibility to improve to control the crack growth and crack propagation in complex structures, controlling the geometry of the structure and controlling the relative density of the specimens. So actually, we can create with bio-inspired design, dealing with the conflict between strength and toughness, which are usually conflicting properties. We can create materials that are strong enough and also tough enough. And we can create innovative solutions that will provide really improvement, a very strong improvement in the mechanical properties of the materials. And actually, we can completely change the paradox in Ashby diagram, creating new materials and new design spaces. The aim of this study that I will present today is to solve the same paradox dealing with the fatigue loading, and actually open almost a new research field, which is the bio-inspired fatigue design that was really not touched much from our community, despite some particular and few researchers that have worked on that. And so nature is able to produce complex structures that actually automatically and are able to survive to cyclic loading. And in particular, I want also to mention that, for example, there are some specific interlocked structures that are created to increase the contact of surface of the interface to improve the fatigue strength and fatigue life of components. So the question that we put and that we ask to ourselves in this project was how we can actually create a new generation of super resistant structure with bio-inspired design. And the aim of this project is, and the name of this project is Butterfly. So we have also obtained some preliminary results, and what it is important to mention is that dealing with fatigue loading, we start from some empirical solution. After that, we went through some theoretical proposal and solution. Now we have the advantage of numerical solution. But if you consider what we have we have really now is that we can see fatigue in a new data-rich world with data-driven methods. And another important point is that if you consider fatigue issues, and in particular bio-inspired design, there are three ingredients that you have always to consider to make a proper design. So the first point is to consider the metastructures or the geometries of your components that can be very complex. And actually, if you see natural structure, they are able to tune the structure and to compose the material in a way to increase and improve the property where it is necessary to guarantee the best property for and the best resistance for the material. After that, it is important to consider the constitutive laws because also for, especially for natural and bio-inspired design, this is a fundamental point. We are not only working with linear elastic materials, but sometimes for improving the properties, nature is able to provide very complex constitutive laws. And after that, the third important point is the load sensitivity, so the capacity to undergoing a different complex loading, especially multi-axial loading, which are typically in real structure. We have also published some preliminary results dealing with these topics. So dealing with this bio-inspired design, one of the best possibilities that we have is to consider cellular materials, which are really bio-inspired complex structures. And in these slides, we see some examples. What it is also really important is that we can actually not only tune the geometry of the specimens or of our components, but actually we can tune or control the structures of the material itself. And this is a quite very good example of what I mean when we consider hierarchical structure that up to now has been used only for solving the paradox between strength and toughness up to now. And you can obtain materials like that, which are with a kind of density that is changing and with the gradients in the structures, and that can allow actually to improve substantially all the properties that we in comparison with the classical with classical steels, increasing substantially the strength and also the yield strength and also the toughness in parallel, which is quite difficult for standard components and materials. So dealing with the cellular materials, we have metal additive manufacturing, architect cellular material, which is the topic. Of course, when we have architect cellular materials, we have complex geometries. And the complexity of geometry also induce issues because we have structural integrity issues, especially related to the fatigue problem. And so the main point is that we need to be able to, if you want to use these structures for real application, is to understand how these structures are able to be sensitive to the defects and how they react to the presence of defects. So the first thing that we did was to design, to study very simple geometries for designing lattice-based components. And the main aim was to create a design FEM that they can provide two requirements, but more complex the component is, the more intensive the simulation will be. So it means that if we want to study these complex components, we need to have a very strong computational efforts, which is sometimes impossible for real applications. So are there any alternative approach to that? So what we tried to do was to create a simple model to represent these cellular structures. And in particular, we proposed inside this project a compensate beam model that was actually set up and also validate to show that it was able to fit the real behavior of the real lattice structure. So a numerical experimental validation has been conducted comparing the compensated model with the homogenized model. And so what we obtain is that actually there is very few variation. If you see the graph on the right side of the diagram, a very small variation between the homogenized model and the lattice model, beam control model. So the outcome is that the compensated beam model is found to provide comparable results to the homogenization. So another important point is that dealing with these cellular structure, in particular dealing with fatigue loading, but also with static loading, what is missing is a kind of lack of standardization for the sample that we need to use for the specimen. So what we tried to do as second step was to create a standardized sample which allowed to have failures in the middle of the specimen, always repeatable for different geometries of lattice. So we study properly the problem, and actually the idea was to have a computational efficient simulation for complex structures. We use the strain energy density approach, which is very good for studying the nodes of this structure, which are the critical point, where we can consider a volumetric criterion. We have the advantage that the criterion is mesh independent, so we don't have to take into account the mesh refinement. And we have a robust estimation of the stress distribution if we first consider the strain energy density and later the stress. So we design a new specimens with a kind of density that was varying along the length of the specimen itself. We study numerically the problem to optimize this kind of specimen. And after that, we went through the experimental setup with the DAC to check if our predictions were correct and if the specimens were failing where we proposed according to the numerical models, and comparing the numerical results with the experimental results under static loading and now also currently under fatigue loading. So dealing with these fatigue-related issues still remain an open problem, and microstructure and process-induced effects plays a fundamental role. So as third step of this project, what we did was to study the behavior of the thin strut of the component, and after that of the strut junction of the components, to have, to have an understanding or a quite good understanding of the critical part of the lattice material. So here it's really a summary of what we did, but it's only for a kind of overview. We made the test for fatigue thin strut specimens, controlling, changing also the mean stress, as it was presented already by Simone Mucchi in another session on Wednesday. And we have seen a very, very strong influence of the mean stress for the thin strut specimen that suggests us that this is a very strong and important effect that we have to consider for lattice structure. And after that, we study also the junction, which is the critical point. So the node is always a critical point for fatigue issues because we have the variation of the geometrical features, and there you have the maximum of the stress concentration factor, and there you have the initiation of all the cracks that are affecting the final failure of the lattice structure. Also there, we made a very, very huge experimental campaign that is only summarized with this slide for lack of time. But the results have shown that the failure near the node is happening when we increase the building orientation angle, and the failure in the gauge length is more statistically more probably more is happening more frequently when we have a building angle that is decreasing. So another point that is quite important is design, manufacturing, inspecting, and prediction, testing, of course, but how we can connect directly design and prediction, because that is the final issue for an engineer, right? So we want to have a design, and we want to have a final assessment or final prediction of the structure, avoiding useless calculation and avoiding useless finite element methods or computational models that are too expensive. So what we did is to propose a synthetic CAD model. So the idea is that usually when you have to consider this kind of lattice structure, due to the fact that the surface is strongly affecting the failure, you need to have a CAD model that is able to reproduce your structure, the surface roughness, and start to study that from a very accurate point of view. But this is very cost expensive, and actually what we want to do is to create a simplified model. And the simplified model is a kind of synthetic model, which is substituting completely the CAD strat model. So we want to create a kind of artificial or substituting model that is able to substitute completely the necessity to do a CAD, a kind of CT scan analysis of your specimen. And so we propose a CAD strat model framework that is based on the profile extraction, waveness and roughness, 3D spline generation, that can do without making any CT scan, which is very expensive and very time consuming. So the results, I will not go inside much the topic, but the result is that if you consider the comparison between the CT scan and the CAD strat model, you can find that the CT scan and the CAD model, if you see where they stop, they represent exactly the specimen. So we reach a level that the CT scan and the CAD model were able to match each other without mistakes. And this means that we bypass completely the necessity of a CT scan for this kind of lattice structure. After that, we also went to the life prediction or fatigue life prediction of this structure. And also here I will be quite brief and short, but we proposed the strain energy density that is quite efficient because, as I mentioned before, it's not sensitive to the refinement of the mesh, and the results are quite accurate also with coarse meshes. And so, first of all, we evaluate if with the CT scan model and with the CAD model, we were able to check and to find the real initiation point for the fatigue failure in this kind of structure, and actually it works. It works not very well only for the 90 degrees sample because the orientation is very extreme and we still are improving the model, but for the 45, 15 and 0, it is predicting quite perfectly the initiation point of the crack. And after that, using the strain energy density, also here I will not go much in the detail, we were able to summarize all the data from different orientation angles and from different geometry inside the same scatter band, providing a kind of master pool for lattice materials. So what's next? Next step is actually to have the help of a kind of statistical equivalent artificial intelligence generate models that will help us also to bypass the finite element models that are time expensive from a computational point of view, that are able also to provide a very good profile and description of our lattice materials. So the idea is to create a statistical database to make a point cloud generation, make a surface mesh generation, make a finite element analysis, but this is not sufficient. Actually, only considering the continuity between the parts is possible if we use the artificial neural network that can learn the relationship between the generated strat and that is able to make a better matching with the real surface and with the real roughness of the real structure. Okay, so the pipeline of the artificial intelligence model is that we have selected is this one. We have selected a non-adversary network plus a genetic algorithm. I will not also go in the details of this, but I have the papers will be available soon, so you will have all the material ready. What it is quite interesting is that with this artificial intelligence generate profile, we were able actually to obtain a fantastic results that is matching the CT scan results almost perfectly. So after that, the main steps that I mentioned before is that we have placed fatigue in a new data-rich world, which was one of the aim of this project. Prediction of fatigue from a process parameter. Huge data sets are required, of course, for reliable results. There is a lack of well-structured data set from literature on IM fatigue. It is quite time-consuming from an experimental campaign, but we want to build and validate this neural network architecture, starting from FDM prototypes that are not very expensive and easy to print, where we can study the geometrical features of these lattice materials. And after that, retraining, what we obtain in terms of artificial intelligence and network for the geometry, also to metallic materials with a smaller data set. And so we start a very huge experimental campaign with more than 4,000 specimens, where we have studied different kinds of materials, polymeric materials, and in particular, we apply the algorithm that is reported here, is a NSGA3 genetic algorithm for the final static and fatigue prediction of this lattice material. So we start from very simple specimen, and after that we increase the geometrical complexity to the lattice structures, studying also what is happening geometrically and studying the macro and micro defects that are happening inside our structures. And as you can see here, we had different input parameters that were used during the test. More than 4,000 results are available on this material. And if you consider the final prediction that we were able to do, it was quite good. It was the first trial that we did, and so we were quite happy of the results. The artificial intelligence, and in particular this genetic algorithm, was quite successful to predict the final failure. So, as last part of my presentation, I want the scientific part is finished. I want only to remember you two great losses for our community. I have the luck to work with them both. George C. I worked with him for more than 20 years. He was one of the father of mixed mode fractal mechanics, together with Fazil Erdogan and other people in the AI University, which was the center probably of fractal mechanics at that period. And I want to remember also Les Cook, with whom we developed a lot of three-dimensional fractal mechanics that Professor Van Lee Guo has introduced to you in the first lecture, in the first plenary lecture of this conference. So I want to remember these two great researchers that were also very, very important friends for me. So everything is still ongoing here. So I do not have any real conclusions, fortunately, because we have still the possibility to work on the topic. There are some partial conclusions that you can read here, and I'm open for questions, but not too many.